Good morning, everybody. So today let's look at a question from Form 5 Chapter 6 Nuclear Physics. Now, if you want to get the PDF version of the question, just head to the description box down below. So let's have a look. Diagram 4 shows part of the uranium-238 decay series. So we have uranium-238 decaying into different things, okay? All the different processes until it reaches the end, which I think this is radium lah. Okay, radium-226. Now, question number 1, what is meant by radioactive decay? Okay, so radioactive decay doesn't happen to everything. Okay, not everything will undergo radioactive decay. Only unstable nucleus will have radioactive decay. Okay, so this unstable nucleus, they can either be too big already, too large, or they can have maybe like a unbalanced neutron and proton. Okay, so all these unstable nucleus, right, when they want to become more stable, they will have to give off things. They will have to release things to become more stable. Okay, so those things are radiation lah, right? So radioactive decay is when, or you can say it is the process of unstable nuclei. Nuclei is basically just the plural of nucleus. If you wrote unstable nucleus, never mind one, okay? It still can be correct. So the process of unstable nuclei becoming more stable, okay, becoming more stable by doing what? By giving off, or the word for that is emitting, okay? Emitting means give off radioactive radiation. Okay, the process of an unstable nucleus becoming more stable by emitting radioactive radiation. Now the next question. Based on diagram 4, determine the number of alpha particles and beta particles emitted when uranium-238 decays into radium-226. Okay, so for this kind of question, right, you must first know what is an alpha particle and what is a beta particle first. Okay, so in case you didn't know, alpha particles, they are 2 protons and 2 neutrons. Okay, 2 protons and 2 neutrons, which we can write it as 2, 4, and alpha lah, okay? Or it is actually also known as helium nucleus. Now for beta, beta is 1 electron, which we can write it as 0, -1 E, okay? Yeah, so this is how you write the notation for alpha, and this is how you write the notation for beta. Of course, you can write beta as well if you don't want to write E for electron. Okay, so from what you can see, right, alpha, if you release alpha, it will affect your top and bottom number. But if you release beta, it will only affect the bottom number only. It won't release the top number. It won't affect the top number. Do you understand? So what we can do, right, is we can check, okay, how many times the top number is affected. Because if the top number is affected, then it must be alpha. So 238 to 234, this must be alpha. Okay? 234, 234, this one not affected the top number, so this must be a beta. 234 to 234, again, not affected the top number, this is beta. 234, 230, this one is alpha. 230, 226, this one is alpha as well. Okay? Yeah, so that's all. That's all you need to, that's how you check whether it's alpha or beta. Okay? It depends on what number gets affected. So from here, we can tell that it is 3 alpha and 2 beta particles. Okay? Next question. What happens to the number of alpha particles emitted in 4b if the surrounding temperature is reduced to near freezing? Okay, radiation does not depend on temperature. Okay, yeah, high temperature, low temperature, it does not affect radiation because radiation is just unstable trying to become stable. Okay, it's not because it is hot, it's not because it is cold. Okay, so we can say there will be no changes. Yeah, no changes. Okay, next question. Here they give us quite a lot of information. They give us the mass of radium, they give us the mass of radon, and they give the mass of alpha particle. Okay, calculate the mass defect in AMU. Right, so they only focus on Ra and Rn now, which is, I think, if I'm not wrong, radium and radon. My chemistry is not very good. So if you look back, right? Oh, sorry, it's not written here. Yeah, then never mind. We know that radium will decay into radon, okay, by releasing an alpha particle. You can see this is 226, and then this is 222. You can see U minus 4. And then the bottom is 88, and the other one is 86, okay? So if I were to write the formula, let me see whether they asked to write the formula. Nope, okay, but never mind. If I were to write the formula, I'll write it like this. Radium 22688 will decay into radon 22286 and emitting 1 alpha 42. Okay, this is how you will write the chemical equation. Okay, so the problem is, even though you can see that 222 plus 4 is 226, 86 plus 2 is 88, supposedly these two, they add up, it should become this. Okay, but the mass, right, is actually different. If you actually use the mass number to add them up, you will realize that there will be some mass missing. That is called mass defect. Okay, so let me just show you. This is 226.54. Okay, and then on this side, it will be 222.018 plus 4.003. Okay, you add this up together. This will be 226.021. Okay, yeah, 021, right? So you notice there's a difference, right? Okay, these two are not the same numbers. Yeah, so let me just calculate the mass defect. 226.54 minus 226.021. And I'm going to get 0.519 AMU. That is the missing mass. That is the mass defect. Okay, where does this mass go actually? This mass actually didn't disappear, right? The mass just turned into energy. That's where nuclear energy comes from, okay? So that's why they ask, calculate the energy release. Now, how do we calculate the energy? If you go to the formula sheet, you will see this very, very famous formula. Very, very famous formula, which is, where is it? Nuclear physics, right? So here, E is equals to mc squared, okay? So let's write that down first. E is equals to mc squared. Now, E is the energy that's released, okay? M is not just any mass. M is the mass defect. It is the missing mass that turned into the energy. C is, of course, the speed of light, right? And speed of light will always be given to you, yeah? But it would be nice if you can memorize the speed of light lah. Okay, speed of light is 3 times 10 to the power of 8 meters per second. So I'm just gonna put in all my numbers. Okay, now, one thing to remember, the mass must be in SI unit. The mass must be in kilograms, okay? So right now you have AMU. How do you change it to kilograms? So they will tell you as well, 1 AMU is equals to this amount of kilograms. So I just have to multiply. 0.519 AMU is 0.519 multiplied by this, okay? So multiply by 1.66 times 10 to the power of negative 27. C, 3 times 10 to the power of 8 squared, okay? So once you type that into the calculator, times 10 power negative 27, right? Oops, 0.519 times 1.66 times 10 power negative 27 times 3 times 10 power 8 squared. Okay, so you should get 7.754 times 10 power negative 11. Okay, 7.754 times 10 power negative 11. Energy, of course, should be in joules as usual. Okay, next question. If the mass defect in 4D1 decreases, what happens to the energy produced in the reaction? Okay, I think this is pretty obvious, right? I told you just now. The mass defect is used to turn into energy. So if the mass defect decreases, the energy produced decreases as well, right? Energy produced decreases. Okay? So it's actually pretty simple to get the energy of a nuclear reaction. Yeah, just remember that your mass must be in kilograms, okay, instead of AMU. Okay, so if you learned something, make sure to like and subscribe, and let me know in the comments what topic you like me to do more exercise on. Okay, see you next time. Bye bye.